afternoon, everyone. It's my pleasure to have this opportunity sharing some of my experience here with you regarding the wholesale credit risk models and model validation. So for today's talk, I'll start with a brief introduction about myself and some terminologies and knowledge regarding the wholesale credit risk model validation and a few of the most generally used models in industry. And then I'll provide some examples for the loss component models covering 3 components: probability of default, loss given default, and exposure at default. I'll give more details in this part. And in the end, I'll discuss about the modeling for 2 generally used loss reserve measures: expected credit loss and risk-weighted assets. Just a heads up, my slides are not fancy as Gabby's. It's just black, white, and blue. So for me, just as Dr. Ogden mentioned, I'm currently working as a model validator as a member of the model risk management team at Citibank. And I obtained my PhD degree in applied and computational mathematics, advised by Dr. Ogden. And before that, I got a master's degree in mathematical finance from Rutgers and a bachelor degree from Shandong University in China. And here's my email address. Feel free to reach out in case of any question or comments. And for wholesale credit risk, the wholesale refers to large clients, such like banks, government agencies, or large corporations, which is in contrast to retails, which refers to smaller clients like individuals or small businesses. So this leads to some differences in modeling, such as the scope and size of the input data, as well as the risk drivers used for modeling. Just a simple example, for the macroeconomic variables, some generally used ones for the wholesale models may be GDP growth rate, unemployment rate, or stock index return, and this might not be used that much for retail models. So this talk will mainly focus on the wholesale models. And here's the definition for credit risk. It's the potential loss due to the obligor, or we call clients, failing to settle amounts due for payment, which is the largest risk type that most banks are exposed to. For example, if a bank issued a loan for a client, but the client was not able to pay back the full amount because it's default, then the banks may be exposed to some potential losses. Therefore, banks need to quantify and manage the credit risk to ensure they prepared sufficient capital to absorb the loss in the worst scenario. And we'll cover 2 of the measures for credit risk today. And here are some credit risk management techniques. I'll just quickly go through. The first one is the banks need a good selection of the counterparties and products to manage the credit risk. And the second one is the bank would like to restrict their exposure for each counterparties to avoid unaffordable loss. And the third one is the banks may diversify their risk across a variety of different assets from different clients across countries and regions. The fourth one is the credit enhancement, where banks may buy credit protection to enhance the credit quality of their assets, especially for the ones with higher risk. As you can see, all these techniques are relying on credit risk models that are accurate, robust, and efficient. Credit risk models are quantitative approaches that process input into estimates to support the decisions made for managing credit risk. And just as any other models, they include 3 parts: the input data, model methodology, and model output. And when we are using the credit risk models, we need to manage the model risk, which is our main duty as a model risk management team. So the model risk is the potential for the consequences from decisions based on the incorrect or misused model outputs or reports. And this can lead to severe loss for the banks, including financial loss and reputation loss. And the model risk are mainly due to this following two factors. The one is the foundational model error that produce inaccurate output against the model objective or intended use. For example, any errors in the formula or any implementation errors that makes the model output inconsistent with expectation. And the second one is improper use or misunderstanding about the model limitation and assumptions. As you can imagine, any improper assumptions on the model may lead to unexpected model outputs. So the Federal Reserve and OCC, Office of Comptroller of Currency, issued this guidance, SR 11.7, for banks to use to manage their model risks. And under this guidance, there are 3 layers for the model risk management framework. The first layer is model development, implementation, and use, which includes the development of new models or incorporating any proposed model changes to existing models, as well as their implementation, and the model use under different scopes and purposes. And for the second layer, model validation, we conducted activities in these 3 aspects. Let me introduce one by one. The first one is to evaluate the conceptual soundness of the model, where we assess the quality of the model design and review the model documentation to make sure the choice of the final model is proper under its intended use, including the process and control of input data and the variables used for this model. And the second one is outcome analysis, where we perform a variety of different tests to assess the model performances, such as comparing the model estimate to the actual observations, or comparing the model outputs with benchmark approaches outputs. And the third one is ongoing monitoring, which is conducted quarterly, semi-annually, or annually based on the risk level of the model, and is conducted throughout the whole life cycle of the models. In this part, we mainly want to make sure the model performance is as expected, subject to any changes in the input data, the clients, and the market conditions. So the third layer is governance, policies, and controls, where we need uniform and comprehensive standards to make sure all the model risk management activities are conducted as expected, and any potential concerns can be identified and dealt with in time. Okay, then next, let's go through a few general examples for the models. I believe these models are not only generally used in financial industry, but also in other industries, supported by Debbie's talk. She just used one of these models in the biomass research, so you'll see. The first one is linear regression models, where we have a set of independent variables, x, and a dependent variable y, which is also called a variable of interest that depends on the value of x. So here we assume the relationship between x and y is linear, given by this formula, where a and b's are constants, or also called coefficients. And epsilon is the residual error. We usually assume each ID normal. And in the general modeling procedure, we would calibrate the coefficients a and b based on the observed value of the independent variable x and dependent variable y. And after that, we can estimate the value of y based on the calibrated coefficients and the projection or forecast of independent variable. So the second one is logistic regression, which has similarity and differences as the linear regression models. So here we assume the relationship between the independent variable x and the logit or log odds of the dependent variable p is linear. So the log odds of p is defined by log of p over 1 minus p. So we can easily get this expression for p through an exponential function based on the value of the coefficients and independent variable. So you can see there's one of the main differences between linear regression and logistic regression is that for linear regression, the dependent variable can take any value between negative infinity to infinity, while the dependent variable for logistic regression takes value between 0 and 1, which fits in the range of the normally defined probability. And the third one is classification models. I think it's also one of the clustering models that we mentioned. So these classification models classifying the data into k groups depend on the independent variable x. So it's a supervised approach such that the points in any group are more similar to each other than any other points that outside this group. So the most trivial case would be k equals 2, which is a binary classification, where we can regard this dependent variable as an indicator variable. Let's assume it takes value 0 or 1. And here I show some example approaches to conduct this classification. One way is through logistic regression. So the probability of the dependent variable falls into one of these two values is given by this formula. And another approach could be k nearest neighbors method, where the assignment of the dependent variable is according to its k nearest neighbors, where they are defined as the k points who has the minimum distance to this point with certain metric. Okay, and next, let's take a look at the loss component models. So the first component is called probability of default. So you can understand its meaning based on its name. So the PD models are used to estimate the probability that an obligor or client will default during a given time period with a known initial credit rating for this client or obligor. So the rest model example is based on this reference, which has an easy implementation through the built-in MATLAB function. As for input data, we use some facility attributes from the portfolio data, such as the initial credit rating, years on book, default indicator, as well as some macroeconomic variables, such as GDP growth rate or market returns. And here's a note for the variable selection process in practical, where we not only need to consider the statistical significance or sensitivity of the variable for the modeling, but also is subject to economic intuition, data availability, which are based on business experience and some practical constraints. And for this model, we use logistic regression, where y represents the log odds of the probability. In other words, it's log of PD over 1 minus PD. And based on the actual data, we can calibrate the coefficients A and B. And then we can estimate PD based on the calibrated coefficients and the forecasted value of the input variable x, the input data or independent variable x. And the second component is loss given default. The LGD models are used to estimate the percentage of an asset outstanding balance that is expected to be lost or cannot be recovered at the time of the client's default. So here I can give an easy example to help you understand the terminology LGD. Assume a bank issued a loan to a client with total amount as 10 billion, including the principal, interest, and any other fees. And let's assume the maturity is 10 years. This is a 10 years loan, but this client is unfortunately default at the 5th year, while it only pays back, let's say, 50% of its debt. So in this case, do you think the bank's loss will be the rest 5 billions? Not necessarily, right? Because just imagine we will initiate a mortgage. The house itself is used as the collateral to offset the risk of this loan, right? So similarly, let's assume this client used 3 billion collateral, and the bank is able to sell the collateral to gain 2 billions to offset the loss. So in this case, the bank's loss for this loan is only the rest part, which is 3 billions, right? So the loss given default is just 3 over 10, which is 30% instead of 50%. That's why we need models to estimate the loss given default, the percentage. Okay, and here's the reference for this model example. And we use some similar structures as the input data. Use some facility attributes like loan to value ratio, investment type, etc., as well as some similar macroeconomic variables as the PD model. And for model methodology, here we use a two-stage models where we separate the case with positive LGD or positive loss from the cases with no loss. So the stage 1 model is a binary classification model where we predict whether the LGD will be positive or not. So this indicator takes value 0 or 1. And the stage 2 model is a logistic regression model that predicts the percentage, the LGD, through this formula. And the final output would be the expected value of these two models, which is just the product of the indicator function and the LGD. And the third component is exposure at default. The EAD model predicts the amount of loss for facility at its default through CCF, which is credit conversion factor. Is defined as the ratio between the additional use and the amount that could be used. And let's use the credit card as an example to illustrate the CCF. So assume I have a credit card with $1,000 as the credit limit, which means for each billing cycle, I most use $1,000. And at current time, I've already used $400. And I didn't default currently, but let's assume I defaulted before the end of this billing cycle. And the CCF is computed by the additional use I made after this current time point, but before my default, divided by the amount that I could use, which is $600. So let's assume I used additional $300. Then CCF is given by 300 divided by 600, which is 50%. And we need this estimation on the potential use to forecast the total amount at the time of default, because it's an event in the future. So here's the reference. And for the input data, we use some attributes like utilization rate, credit limit, and drawn amount. In my example, the credit limit is $1,000. The drawn amount is $400. They are all the amounts at the initial time, as well as some macroeconomic variables. And here we use a linear regression to estimate CCF through this equation, where CCF can take values less than or equal to 100%. For the value CCF being negative, you can understand it in this way based on the credit card example. Instead of use additional amount on my credit card, I actually paid off some of the amount instead before my default. In this case, the CCF will be negative. And of course, the clients could pay as much as they want before their default, so the CCF can go to negative infinity, although in practical, it's not very possible. And after we estimate CCF, we can compute the EAD value based on this formula. So you can easily understand based on my example for the credit card. is given by the drawn part at the initial time, plus the CCF measures the additional use, the potential additional use, times the unused part. Okay, and next let's take a look at two loss reserve measures that are calculated based on these three loss components we just mentioned. The first one is called expected credit loss, which is the average credit loss expected for a portfolio over a specified time period. So it's estimated based on these three loss components we just discussed and discount factor. So for each asset, the lifetime ECL is the sum of all the ECLs of all time periods before the expiration time, which is given by the product of marginal PD, which means the probability of default in this specific time period T, and loss given default and exposure at default. And then this product is discounted by this factor based on the effective interest rate. And if we sum up through all the time period, we got the ECL for this asset. And as for the portfolio ECL, it's the simple sum of the ECL for all the assets in this portfolio. And the second measure is risk-weighted assets, which is a bank's assets weighted by their risk level. There are multiple ways to estimate RWA, and this approach is called advanced RRB approach, defined based on the Basel II capital rules. It's given by a function of PD based on the normal CDF times LGD and CCF, and then timed by a constant A. A is defined under the Basel II rules. And that's it. Yeah. And here are the references I used for today's presentation, among which these two are online resources. You can easily try it out through the built-in MATLAB functions. And that's all of my talk.
Are there any questions? How effective are these linear models in predicting risk?
They are actually one of the most important ones used in industry, and they are pretty effective. Although I know it looks not as fancy as the ones we used to use or practice at school, but one main difference is the real problem is based on the real data. So the model developers spend lots of time to process the real data and to maintain the model. As I mentioned, there's online monitoring after the developed model, because there are changes in many aspects. So we have to make sure the model is still predict as expected. So sometimes the easier the model, the better effect it is. Yeah.
So it seems like classical machine learning stuff. So once you select the variable, so do you do any post diagnostic of which variables are really significant? Because before modeling, you select some variable, and after modeling, do you do any diagnostics to see if they're really significant variables?
Yes, that's a good question. So during the development stage, we may need to use the standard statistical methods, like the significant level is to see the variables selected are statistically significant. And after that, there are multiple judgments. One is based on the business experience, to say that's pure practical, to see if these variables are intuitive. And other tests are like more general tests on the model performance. Instead of to see each individual models, we may need to see, like, for example, the sensitivity of the model outputs to the chosen variable, or in general, the model performance benchmarked with the alternative models or the actual data to see how the model performs. Yeah, and it's also subject to double check upon the refreshment of the data set to see if the chosen variables need any adjustment.
Any other questions? Well then, let's thank the speaker.
Thank you.